Okay, now can you hear me, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. So, last day, I mean, in the last week, mm, we talked about mm, three important things which relate to the point-to-point digital communication system. So we said, okay, if we have this input source as a random variable, which we denoted as x, and then the output is y. Okay, and this is the channel. So we talked about three basic concepts. One is hx, which is the entropy of the random variable x, which is the input source. And we talked about hy, which is entropy of the random variable y. And we also said what is the conditional entropy. So y given x. So this is the conditional entropy. Say initially, so what do we mean by a channel? Okay, initially what is given to you, since the thing we have to understand here is we always define entropy of a random variable x, but when we use the formula to define it, so we only used the probability distribution, not the probability mass function, because in our case the random variable is always discrete. So we only used the probability mass function associated with the random variable x. So basically, whenever we say then hx, I mean the entropy of a random variable, so what we actually mean is that it is the entropy is a function of a probability mass function corresponding to x. Okay, so this is just to note that entropy, okay, or just write entropy is a function of of the probability mass function associated to x, or just write it probability associated with x. Okay, associated with x, and what it means, we said okay, it kinds of, it is a measure which measures uncertainty of x. Okay, but okay, we said okay, we as we go along we'll see like why it is, but if we want to interpret it right now, so we can interpret it like this way, that entropy is something which quantifies the uncertainty about the random variable x. And then we also said what is a channel. We said channel is characterized by some conditional entropies. So I used a different notation just to emphasize on the fact that okay, so whenever I said x, so that means x has some alphabets, or let's say some symbols, let's say a1 2 dot 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 some ak or aj, and or I think we denote it as ak, and then and this y, let's say okay, this is y and this is the alphabet or the symbols are, let's say one b2 b1 b2, let's say bj. Then what is given to me, that this p1 p2 pak, like the probability mass function I said with the x, so this is known to me, so which is a probability distribution p of x is known to me, or let's say pi ai, okay, I equal to 1 to k, this is known to me. And by channel, we mean, okay, it is a set of probability, conditional probabilities. So we can say the channel. So this is the input, which is characterized by this random probability mass function, and the channel is characterized by all the conditional probabilities, like what is the probability of obtaining bj when or receiving bj at the receiver's end, which is given by y. So when ai is set, okay, so or ak is set, let's say. So this is what is a channel. So a channel is nothing but a set of conditional probabilities. And if we know this too, okay, so whenever there is a point-to-point communication system and you're talking about sending an information, here you can ask, okay, today I think towards the end of the lecture, we'll be able to start talking about coding theory. And then you will see that we'll say, I mean, what we actually meant by saying A1, A2, AK. For the time being, we assume that they are just like alphabets, just the letters. And you want to send a combination of like you want to send, let's say that the sender wants to send, let's say a word, okay, a word like any word. So a word is nothing but a, a sequence of the alphabets of the letters. So A1 to AK can be considered, let's say, A to Z, and you construct a word out of it. That means you actually want to send a sequence of these letters, okay. But since there is a noise in the channel, so which is characterized by these conditional probabilities, so each word consists of some letters. But whenever, let's say, you intend that the sender intends to send a particular letter, let's say A, but it may get flipped, and the receiver can receive something else. Okay, that can happen, and that happens due to the error of the channel, and these are given by the probabilities. If this probability is high for some particular value, then we can assume that okay, that there is a high chance this bj can be obtained whenever ak is set. Okay, yeah, then we said what that this probability, both the probabilities are known, like the PMF for the. So why it is PMF? Because we said okay, all the letters when you are constructing a word, let's say, okay, let's say English word, so English dictionary word. So when you are constructing a word, so all the letters in the word, okay, do not occur randomly. Like you cannot just put some random letters and you can construct your word. So we said, okay, each letter will occur with some probability because there is already a probability distribution, which explains the occurrence of a letter or the chance of occurrence of a letter in a word. Okay, which you defined it as like the number of words which consist of the letter divided by the total number of words in the dictionary. Okay, so yeah, so each letter can occur with some probability, and that probability is given by this PMF, the probability distribution of capital X. And then we have this channel, which is a set of conditional probabilities. And using these two probability distributions, we defined a probability distribution for Y. So then using let's say Px and Pxy or Py given X. So we actually introduced a new notation. Instead of Pyx, we actually wrote Wyx just to emphasize on the fact that this P is nothing to do with this P. So this P and this P, they are different. But since it is probability, so you are writing P, but it has nothing to do with this P. So this P, okay, has so the P, let's say Y given X, which describes the channel, and this P, Px, okay, and this is nothing to do with this P because it is probability. So that's why we said, okay, instead of this P in the conditional probability, you can just write Wyx in order to emphasize on the fact that this is just a set of conditional probability which has nothing to do with the initial distribution. But when both the things are given, like W conditional probabilities and the input PMF for the input symbols, or the possible inputs, the random variable x, then we can, so using this, we can define, in fact, we defined a probability distribution, a probability mass function for y, and then we show that, what did we show? We showed that, and we showed that, what did we show? We showed that these three things, these three quantities are related. In fact, we actually had shown that h of xy, which is the, okay, you can write x comma y also, doesn't matter. So it is the entropy of the joint random variable, which is exactly equal to hx plus hyx. And from the picture, we had seen that, so this joint entropy is not exactly equal to hx plus hy, okay, but it is hy given x. So it is conditional entropy plus the entropy of x, okay. So although explicitly we did not mention here hy, the entropy of y, but in the schematic diagram, what I think I gave you a Venn diagram kind of a thing where we can relate these things. Okay, we said, okay, if this is, let's say, hy, let's say this is hx. So if we draw like this, so it is, let's say this, let's say this is hx, and let's say this is hy. Okay, this is hy. So this is hx, let's say, and this is, let's say, hy. Then we said, okay, this part, okay, this part can be talked about. Oh, not this part exactly, but okay, that can be done using mutual information. But we said, okay, this part is actually h of y given x. So this is what we defined, and then we actually proved, or I think we outlined the proof of it last day and before that day. And then we said also that this can be generalized a little bit, okay. And in fact, last day I think we mentioned is that if we have n number of random variables, so an extension formula for this, I mean the way you have proved this one, or it can be proved this one. I mean it is just the definition, is not very, proof is very simple. I mean you just need to know the definition of the conditional entropy, that's it. So then this can be proved like this is h of x1 plus h of x2 given x1 plus, let's say, h of the entropy of x3 given x1, x2, and so on. And finally, it can be shown that this is h xn given x1, x2, xn minus 1. So this is very interesting actually. So if you have a cascaded situation where you have cascaded channels, or you have, let's say, a random vector, then the entropy of the joint random variable is nothing but the entropy of the first one plus given first one, and the entropy of the conditional probability, and then the conditional probability when x1, x2 both are known, and so on. Okay, so this is the thing. This is the thing we discussed. Now, today we'll introduce a new concept. Okay, and we'll try to understand what are the mathematical properties of entropy as a function. Okay, and do not forget that we have three main concepts about entropy, which is hx, entropy of x, which is the input source, hy, this is the entropy of the output source, and this is the entropy, conditional entropy. So whenever we are talking about a channel, these three quantities, okay, are the most important things. Okay, so entropy, depending on, say here, for example, the third case, when we talk about conditional entropy, then it is not only a function of x, but it is also a function of y. I mean, yeah, so function, when I say function of x and y, so you can say conditional entropy depends on the conditional probabilities p, y, and x. So definitely h In the third case, H depends on the probability distribution X and the conditional probabilities. And HY, the entropy of Y, definitely it depends on the conditional probability and also the input probability. So the probability distribution of X as well as the conditional probability. And HX, of course, only depends on the probability distribution of X. And we said that these three concepts can be just considered as a concept. I mean, entropy is some number related to a random variable, but it has real physical meaning when it comes to a communication system as introduced by Sana. By the way, I did not I said I'll give you an operational meaning of entropy. So possibly today towards the end of the class or next day I'll talk about that. I'll give you a precise meaning of operational meaning of entropy. I mean, what it actually means when it comes to practice. I mean, what and how it is defined. Here we know how it is defined, but when it comes to practice in the sense of point-to-point communication, then what it actually means. Okay, so now what we'll do is, because entropy is a nice concept, let's say, which will be used in communication theory. So now for us, it is to understand what are the mathematical properties of entropy. Because if we know what are the mathematical properties of entropy, we can probably define entropies of a random variable in a very different way. So first, we need to understand if we define entropy in Shannon's way, then what are its mathematical properties? So basically, whenever we say property, it means what are the properties of these functions H, H, H. So conditional probability, and conditional entropy, entropy of the input random variable, and entropy of the output random variable. Yeah, so now we'll talk about mathematical properties of entropy. Okay, yeah. So whenever I say mathematical about entropy, so entropy depends. Okay, entropy depends. Entropy is defined, okay, as entropy of a random variable, but it actually means entropy of a probability mass function, right? So it depends on the PMF, on the probability mass function, okay, of, we'll always assume like anyway. So let us say entropy depends on the PMF of a random variable. Okay, so that means basically what we want to say that if I consider H as a function, then the domain of the function, okay, domain, and can say that it is this to R, the real line. So it is 0, this is positive, this side is positive, this side is negative. Okay, positive and negative. This is 0, R. And what is the input here? The input here is what is called distribution space. So it's a set of distribution, actually, a set of probability mass functions. So this space is known as a distribution space, but I will not define why it is called a space, because in that case I have to define many things. Okay, the basic difference between set and space is a space is a set with some additional structure. Okay, that's why it is called a space. For example, you might have studied metric space, vector space, okay, anything when you have topological space. So whenever you say it is a space, that means it is a set, and on top of that there is an additional structure, okay, which is defined there. So this is called a distribution space, or we can just assume for the time being this is set of all PMFs. Okay, whenever I say set of all PMFs, then the question is what kind of set is this? How do the elements interact? For example, if we take, can it be a vector space, for example? Like if you take two PMFs, can we add those two PMFs and can I create a new PMF, something like that? And if we scale a PMF, let's say, can I still get a PMF, and so on? Okay, so we'll not talk about that here, okay, but you may ponder about, I mean, you can see like what happens. So we'll not go into the this thing. Just we'll just prove the property of H here for the time being. Okay, we'll not go into discussing or defining all the properties of the distribution space. Okay, if you are interested, you can study that, but we'll just focus on what is only one particular property of the entropy. So we're not talking about, we'll not be talking about distribution space. Okay, this is a space of the set of all probability mass functions. So the main property will in the main property of H is something called concavity. Okay, let us first define what is a convex function. Okay, and then we'll talk about concavity. By the way, whenever we are saying it is a PMF, okay, so basically it is a vector. And why is that? Because let's say my possible similar sample space. Okay, so let's say let X be the sample space of a discrete random variable. Okay, then if I have X, okay, which is defined from, this is a random variable which is defined from this, then we can say that okay, X of Si may be the sample points, which is equal to, let's say, Xi. Okay, let us assume that this way. And whenever I say I, so I can be, so here, let's say, where S equal to, let's say, S1, S2, and so on. So it could be either, so because it is a discrete random variable, so it is either finite, the sample space S is either finite. Okay, so here let us confusing notations. So let us say, so this set S, okay, so it is either finite or it is countably infinite, meaning it is infinite and countable. So then I can say I equal to here, I equal to starting from 1, 2, and so on. Okay. Okay, then once you do that, then what is the PMF? What is the probability mass function corresponding to X? It is nothing but probability of X equal to X. So this is the PMF, right? So this is the PMF. Okay. But if it is a PMF, so what it means? So here the sample points are, let's say, these values are, let's say, corresponding to sample points, okay, are just x1, x2, xn. So we can write this PMF, okay, this function as a vector, which is, let's say, first entry could be f of x1, which is f of x2, and so on, right? It goes on. If this is finite, then this is a finite dimensional vector. I mean, the sample space is finite, then it is, which is equal to, you can say, this is probability of x equal to x1, and then probability of x equal to x2, and so on. In fact, this is a non-negative vector because all these values, okay, the entries, okay, fx1, fx2, and so on, are probability of x equal to x1, probability of x equal to x2. All these entries are non-negative, so we can say that it is a non-negative vector, and we can say it is a non-negative vector of dimension n if the sample space contains n number of possible sample points or possible outcomes. Okay, so although we say it is a PMF, it is a function, essentially it is a vector. Okay, so now so here then, whenever we are talking about entropy as a function, here we can say that this is a set of vectors. A set of vectors. It could be finite dimensional, infinite dimensional, but it is a set of vectors. I mean, finite dimensional meaning finite dimensional vectors. So vectors having only finite number of entries, and infinite vector meaning it has infinitely many entries, like I defined. So set of vectors, okay, depending on the sample space. So now we want, yeah, anybody wants to say something?
Sir, actually, I want to ask you about. So at max, we are taking the vector to be countably finite, countably infinite.
Yeah, so we are talking about discrete random space. Yeah, discrete random variable. Yeah.
So officially, everything in the distribution space is a tuple, like infinite tuple at most.
Yeah, vector.
Okay.
Because if you do not consider it as a discrete, if you consider it as a continuous random variable, we cannot talk about vector representation of that. Okay, because if it is uncountable set, the sample space is uncountable set, we cannot explicitly mention what are the entries. Like we cannot write it this way. We cannot write sample space this way. S1 is 2. We cannot arrange them. Okay, let's say because it is not countable infinite. Since it is countable that infinite, that's why we can write it like first element, second element, third element, and so on. Or maybe not the first, but let's say some elements. Okay, like S1, S2, S1. Whatever. We can identify an ordering. We can define an ordering. Okay, because it is countable, so it has a one corresponding with a set of natural numbers. So we can write it like S1, S2, dot, dot, dot. But in general, if it is uncountable, we have to treat it like function. That's why I said will not. My focus in this course is not on continuous random variable, because we have to deal with that in a different way. Let us say we have, I mean, this is what happens in one-to-one digital. I have seen that suppose we want to say in a point-to-point digital communication system, okay, in a practical system, let's say, okay. I mean, let us not go into the more complicated things, but in a brief understanding or in a broad understanding, we want to send, as the sender wants to send some symbols, and number of symbols could be at most countable infinite. Okay, so if that is the case, then X is always a discrete random variable. Yeah, so this is a set of vectors. Okay, this space, distribution space is actually a set of vectors. Okay, so whenever I then want to define a property of this entropy as a function, then I have to define some kind of property of a function whose domain is set of vectors. Okay, so let me first define, I mean, you should know this, but let me, for the sake of completeness, let's say, let me first define what is called a convex function. Okay, so because we want to prove that entropy is actually a concave function, so let us talk about what is a convex function. And here we can assume that also that everything is finite dimensional. So even not only this is discrete random some random variable, but we can also assume that it's finite. Okay, just to make everything very, very precise. But it can be defined also for indeterminate space and so on. Okay, so let's say we have finite number of symbols. Okay, which we want to transmit. The sender wants to transmit to the receiver. Okay, that also you can assume. So let's say, so this is what is called a convex function. Okay. So let us define what is called a convex function. So we have a function. So let f be, okay, let f be a real valued function. A real valued meaning the value is a real number. So real value function. Okay, function defined on. So I'll not be very mathematical when I'm defining it, because okay, let me just define real valued function defined on any like k-dimensional vectors. Let's say k-dimensional vectors. It's a real vectors. Okay, okay, which form a convex set. So there is also a concept called convex set. I think you should be knowing that. Okay, so here also I'm assuming that set of this space is also convex. Okay, convex meaning geometrically speaking. So set, okay, if you take any two elements of the set, so there must be a concept of addition which is defined, and if you add them up, let's say, which is here, still here, so means so this is like, yeah, so this is what is the basic understanding of a convex set. But later I will not go into, because this is very elementary. Okay, so you can define anything like convex set. So all this addition, this and that, everything has to be defined. Okay, So which form a convex set, let's say, and then we say, okay, then f is said to be a convex function if you can say f of lambda 1, let's say some x1 plus lambda 2, or maybe I can write it capital letters. Okay, x1 plus lambda 2 x2. This is always lambda 1 f of x1 plus lambda 2 f of x2, where I mean in place of lambda 2 I could have just written 1 minus lambda, but anyway 1 minus lambda 1, but anyway, so where lambda 1 is bigger equal to 0, lambda 2 is equal to 0, and lambda 1 plus lambda 2 is equal to 1. So if you want to see this, as we discussed before, so if you want to see this is a R2R function, that means it is k is equal to 1, then you can see that it is a function like this. Okay, let's say this value is x1, this is, let's say, x2. So this is some point lambda 1, this point lambda 1 x1 plus lambda 2 x2, because this is nothing but lambda 1 x1 plus, or let's say capital X1, and 1 minus lambda 1 x2. So this is a convex combination of x1 x2. That means it is a point, it is a vector which is lying between x1 and x2. Okay, so in case of real numbers, let's say it will be somewhere here, and then this value, this is the functional value of that. So this is, let's say, x, and this is x. So this value is less than or equal to sum of this plus this. I mean, if you just take this, this is fx1, this is fx2. So then this point is actually lambda plus lambda 2. I mean, this point means this corresponds to this number. Okay, and this point is coming this number on the y-axis. Okay, so of course this value, okay, this value is less equal to this value. Yeah, so this is just a two-dimensional interpretation of picture of it. Okay, but here we are talking about k-dimensional vector. So domain is a k-dimensional space. So for example, if you have seen a boat, so it's like a convex function. If you consider like a boat is lifted above, and its shadow, let's say, on the sand or on the plane, okay, is the domain, okay, kind of a thing, then it is kind of a convex function. Okay, so yeah, so that is an example of a convex function. And this function, I mean, just to mention that if a function f is convex, then minus f is concave, or a function is called concave if minus times that function is convex. Yeah, somebody wants to say something?
Sir, actually, when we are defining this function, you wrote like f is a real valued function defined on k-dimensional real vector space, which forms a convex set. So,
No, I did not. So that's why I said I did not define it is a vector space. I said k-dimensional real vector which form a convex set. So I did not say it is a vector space.
okay. So,
I said it is just
real
a convex set.
real vector which forms a convex set.
Yeah. So I don't need vector space here actually. Only thing is that this addition, I mean this has to be defined. So that's why some addition is defined. So that's why whenever I write this addition and the scaling, okay, it is inbuilt. It is the we are assuming that it is defined. That means that's why we said it is k-dimensional real vectors. So the standard addition and standard scaling, they are working here. So yeah. So I didn't say that it is vector space. It is just a convex set. Yeah.
So this function is defined on a convex set. That's it.
Yeah.
And it satisfies the following condition. Right?
Yeah.
Both of them, right?
Yeah. So you are assuming that it is defined on a convex set. Once it is defined a convex set, then only you can say it is a convex function or not. Okay. But the question is, why do we need this to be a convex set? Any idea? Any idea?
So because when we are writing expression on the left hand side, it ensures that if x1 and x2 are in the set, then the linear combination will be the
Exactly.
convex linear.
Exactly. So this function, okay, so suppose x1, x2 are there in the set. But what is the guarantee? This input, whenever I define f of lambda on x1 plus lambda to x2, I do not know whether this lambda on x1 plus lambda to x2 is there in the set or not, but I am using it. So I have to guarantee that it is there so that the function is defined on that. And for that, I need convexity, the convexity of the set. Okay, that's why this convexity, convex set is inbuilt in the definition because of the argument. That argument is something. So because I said the domain is, let's say, set of some k-dimensional real vectors. Okay, but I'm defining the convexity property of the function or the convex function in terms of this f of this lambda on x1 plus lambda to x2. But if x1, x2 are there in the domain, but I do not know whether lambda on x1 plus lambda to x2 are there. So I need to also guarantee that this is there. So that's why I'm assuming that the domain is a convex set. Yeah, that's the case. And so that's why real valued, meaning all this is comparable. So this is a real number, this is a real number. So their sum is also a real number, and this is also a real number. So a real number we have ordering, right? So like if you give me two real numbers, I can say which one is bigger. So this makes sense. I mean, this less equal to makes sense. There is an ordering in the real number. You can say which one is bigger, which one is smaller. Yeah.
Sir, actually, I have one more doubt. Like, why we are restricting ourselves not to make this as a vector space? Because we can always think as infinite tuple, and we can do some wherever the value is present. Other we can assume zero.
No. A vector space, if we assume this set is a vector space, that is a very, I would say, strong condition, because vector space is always infinite. In general, in principle, let's say, because we're talking about k-dimensional real vector. So here the field is R. Vector space is always infinite. Infinite means it is not bounded, okay? But convex set can be just bounded. So this concept, you don't need, for this convexity of a function, you don't need the domain to be an unbounded set. It could be just a finite set, like just a convex set. It is like a square or let's say interior of a circle kind of a thing, or interior of an ellipse kind of a thing, where you have just a finite domain, a bounded domain, okay, and you can still work on that. Yeah, you don't need an complete infinite unbounded domain. So if you can do that, any vector space is a convex set. So that's why there is no meaning of saying convex set there, because any vector space is convex set. So that is a more stronger condition, which we don't need in order to introduce the concept of convex function. So for this condition, okay, we don't need to have the domain as a vector space, and that is a much more stronger condition. Okay, so because the domain can be finite, still this property can be satisfied. For example, in most of the for example, whatever I have drawn here for the case of 2 to C, I can say that this is just a domain which is finite. Okay, not a problem. I don't have to take the entire x-axis as a domain. I don't need that. I just need a convex set which is an interval, let's say. Okay, that is enough for us. So yeah.
Sir, yeah, what is codomain of this function?
Which function? F.
F we define as.
This is real. So real valued
Sir,
function means.
sir, can it be a vector function like Rn to Rn, something like that?
It can be, but here we don't need that. So if it can be the vector value, then we also have to talk about an ordering there. When do you say two vectors are ordered, like one vector is less than other vector, that can be defined, but we don't need that here at least, because we are talking about entropy, and which is a real valued, or maybe, yeah, it's a real valued function. So we only need that the function has to be real valued. That's it. But if you want a vector value, there is a problem with the ordering, because this is the convexity condition and there is an ordering. Then the question will be this f of this, okay, this is a vector. Right hand side you have a vector, left hand side you have a vector. Then how do you define a vector is less equal to other vector? This is not defined, right? In general, I mean, this is not a standard idea, okay? Then you have to define what is the ordering of this thing. And if there you are able to define such an ordering, then possibly you can also extend this. But Here we don't need. In fact, in a general scenario, when we have convex functions, we always call it as a real valued function. Yeah. Anything else? No. Okay. So we don't need much convexity. I mean, a function. We didn't know much about the properties of convexity, this and that. We don't need that. We only need one inequality, which is called Jensen's inequality. Okay, I did not define what is concave function. So I can just say that a function is a function f, let's say, is called concave if minus of f is convex. Minus of f means if you know fx, then minus f of x is minus times fx, convex. Okay. Yeah, so this is what is concave function. But we don't need much. We need only one lemma, which is known as Jensen's inequality, which I'm not going to prove. It is very undergraduate thing. Jensen's inequality. You can find a proof of this in any undergraduate probability book. Equality. Jensen's inequality is the following. Like so let x be a random variable, x be a k-dimensional. I'm writing here k-dimensional because just to match with the definition of my convex function or concave function. Dimensional real valued let's say random variable. In fact, it can be a vector random variable as well. Okay, so it can be a vector also. So real valued. I mean, there is nothing to say about real valued, but I'm just because I define convex function as real valued function. That's what I'm saying. It is always real valued, right? Random variable. And if you have any convex function, if fx is any convex function, any in this world is a convex function, then expectation of fx, okay, is bigger or equal to f of expectation of x. So there are too many concepts involved here. So one is if you have a random variable x, in fact, forget about this. I mean, you can just forget about this vector as well. You can just say it is a random variable. And f of x, whatever the fx, let's say f of x equal to x square, something like that, okay, which is convex. Like f is convex here, by the way. So you can define function of a random variable, right? So you can always define that. So whenever you have a convex function, so like this here, for example, if x is just a random variable which is from R to R, so here you can say if this is my random variable, let's say, okay, so if this is my a convex function, let's say, then you can of course define this f of x, which is a function of the random variable, and then this is also a random variable. So then you can also define expectation of this random variable, and this will be always bigger or equal to f of ex. So what is f? So f is a convex function. So then this must, for example, it is a real number, okay, ex. So f of x will have some value. So, and this inequality is always satisfied, which is called a Jensen's inequality. Okay, so you'll see, I mean, if you just see the Thomson and Thomson book, you'll see that this inequality, in most of the cases and most of the proofs of, let's say, the inequalities, okay, regarding the entropy or the mutual information and so on, okay, they use just Jensen's inequality. In fact, so this has a lot of use, okay, when you are proving some inequalities for this thing, okay. And not only that, this inequality, okay, this can be equal. Some particular cases, this can be equal. So this inequality, okay, okay, can be equal, can be an equality. Okay, can be equality. Okay, only when. Okay, only when. So x equal to ex, if you know what I mean, and then with probability 1, and then you can, and f is also convex and so on. F is strictly convex. So there is a concept of strictly convex as well. Concept of strictly convex means here you have defined this as a convex function. Okay, this guy is less equal to this guy, but okay, so it's the function f is said to be strictly convex if this inequality in the definition here, okay, this becomes equality with lambda 1 positive, lambda 2 positive, okay, only when x1 is equal to x2, then f is called strictly convex. Meaning, with lambda 1, lambda 2 being positive, this becomes an equality if and only if x1 equal to x2, then it is called a strictly convex function. So that means in this picture, whenever this value, let's say it is equal, and this, so this is a strictly convex function. Meaning a convex function can be just a line also. Okay, this is it can also be called a convex function, but this is not strictly convex function. Yes, it is always equality is always maintained. It's not less than. So strictly less means always this line is always above this curve except at the endpoints. Then it is called strictly convex. This is what it means geometrically. But anyway, so yeah, so we need only this part. You know, for every equality holds, you can just find it out. I mean, in your undergraduate textbook. Now we are, yeah. Somebody wants to say something?
Sir, actually, I'm very confused. Like, what is the meaning of like x be a k-dimensional real valued random variable?
Yeah. So basically, here what I mean here is x is like a random vector, and each of them is a real value. I mean, real value. We don't need to. That's what I said. Since here everything we define for real valued functions, so here you can say like this. So that you see, the thing is here I am defining fx, right, and I say f is a continuous. Sorry, f is a convex function. So if f is a convex function, according to my definition, let's say it is all k-dimensional real vectors, right? So a domain is a k-dimensional vector. So that means the domain has to be something which is k-dimensional, right? Otherwise, how do we define that? So then I said, okay, x can be equal to a random vector, which is x1, x2, xk. You can assume that if you just assume that if you just R to R function, let's say, okay, or let's some interval AB to R, then you can consider that is x is just a random variable, not a random vector. So it is like this. And each xi is of course a real valued function, because this is what is required, because whenever I said this k-dimensional real vector, so this is important, real vector. Okay, so xi's must take only real values. So this is, and just in order to make sense of what I have defined here, convex function, because I am applying this thing here, f of x. So whatever I assume about the convex function, so x, the random vector x, also has the same property. Otherwise, you cannot define it. Okay, so all the assumptions are, I mean, whatever assumptions you had make for this convex function, same assumption you can make about the input of this convex function, so that everything is defined. Okay, so that's what it is. Similarly, yeah. So for example, how do you define expectation? So if x is a random vector, how do you define expectation of x? Okay, if x is just only one random variable, it's a number. But if we have if we have n I mean joint random variable, or let's say it's a random vector, then what is it? Is it a number? No, it is not a number. So f is defined, wherever it is defined, it has the same property. And since here in the definition I said k, so that's why I said it is k here and nothing else. So just to make a sense of this inequality. Okay. Yeah. So now we'll not prove three but this is a main theorem. But let's say we'll not prove all of this. I'll give it as homework. But I prove at least. Yeah.
Sir, can you explain just above part? It can be an inequality only one.
Can? What is the question?
Sir, when this Jensen inequality hold equal to?
Yeah, I find it out. Okay, I said it will this this anyway. So in particular, so this let's say, yeah. So this inequality I'm talking about this. So if I give a number, then I can, when I was speaking, then I can say let's star. Okay. So in particular, the equality in star holds only when, okay, this inequality becomes equal only when x is equal to ex. It means if x is a vector, real value, then ex is also a vector if x equal to ex with probability 1, okay, and fx is strictly convex, okay, then this equality holds. And not only that, the vice versa is also true. If this is an equality, that means fx is a strictly convex function and x equal to also ex, okay, with probability 1. So now I have to see, I did not write everything here properly because I need to define all this stuff, but I don't want to define it because I mean, I'm assuming that you know this. So if you don't know it, just read any book. So this inequality is like Jensen Equality is very famous, which we prove in undergraduate text, undergraduate class, let's say. So x equal to ex with probability. What do I mean by saying this? X equal to ex with probability 1. When do I say an equality holds with probability 1? Okay, then I have to explain that also, but I don't want to do that. So we'll assume that in most of the cases we'll not use this, only will use this inequality. So even if you do not know what it means, that is fine. So I only need you to assume, or I need you to know this fact that this Jensen inequality holds whenever you have a function f which is convex. In most of the cases you'll find that, I mean, I will not prove many things, but in like a Thomas book, when you read a proof, you'll see that most of the cases the log, okay, the property of log, is it convex or concave? So that property will be used. Okay, so minus of log, let's say, whether it is concave or convex, that property will be used here. So a lot of inequality. So in fact, here this f is very, very specific, the log function. Okay, so that will be used in our context. So but okay, so all the time we'll mention Jensen inequality, but actually our function will be kind of a log function. Okay, yeah, that's why we need this inequality.
Sir, while writing the right hand side, f of expectation of x. So here we are meaning like component wise expectation of each random variable.
Yeah, whatever way it is defined. Yeah, what do you think? How do we define expectation of x, a random vector? Same
It
thing.
should be like, yes.
Yeah, so whatever I was saying is that whenever, I mean, whatever we define any expression, it has to make sense, right? So here f is a function, okay, which is a real valued convex function. E is expected, and there are too many things. And this x is not only just any vector; it's a random vector, meaning it's a vector of random variables. So everything has to make sense. Okay, so whatever the standard definitions are there. Okay, so I want just you to have a sense that these are all defined, well defined, and then we have this one. Okay. I mean, you'll see whenever, at least I'll do one proof whenever we'll be using this Jensen Equality, you'll see that, okay, how it is used. So it is very simple, although it is, I mean, the definition is, the inequality is very complicated because you need to know all these terms. But anyway, when x is just only one random variable, I mean, just a random variable, it's not a random vector, then it is very simple thing. I mean, it's not a very big thing. Okay, at least for our context. So anyway, so now we'll talk about this theorem, and this theorem has three parts. Okay, and this theorem is the only theorem I'm going to prove, and all others I'll say as corollary or you can prove. In fact, out of these three statements, I'll prove only one, or maybe two anyway. So let's see. So first of all, the entropy. The entropy, as I said, like entropy can be considered as a function now, and it is a function not only about random variable. So if we write even hx, but it, what we mean is that this is h of p, or let's say px, okay, because it is defined in terms of the probability mass function. So even if we say it is a random variable, entropy of a random variable, but it is actually defined in terms of the probability mass function of the random variable. Entropy as a function. So the argument here, you see, argument is a distribution, okay. So is, addition means it is a vector basically, because Px. I mean, if let's say the sample space is finite, then Px is a vector, as we discussed before. So is a strictly concave function. Concave function. Okay. So of what? What is the argument? I need not write the argument because I already discussed. It is that with respect to the power distribution of x. Okay, but we already mentioned this. And second thing is Hy. Okay, the entropy. The entropy Hy. This is also an entropy, but this y is now here in the sense of the communication channel. Okay, y is the output. Okay, random variable, and x was the input random variable. So of this. So now say here, I mean, this entropy is a function of two probability distribution here. One is the probability and the conditional probability W and the probability distribution of the x. So it is like x, and you can say y given x. So yeah. So okay. So it is like, I mean, I'm explicitly writing it because I mean you'll know what I mean. Okay. So Hy. And then why I'm writing this as a product, because this is how it is defined. Okay, product of this two. Why? I mean, this is given last day. I mean, I discussed this last day here. I mean, if we just forgot what it is, yeah, this is Hy given x. This is how we defined it. And yeah, this is Hy given x for a small x if x is given. And yeah, this is what it is. This is how it is defined. Okay, probability distribution on y. So this is, you see, w px times w. So that's why I'm writing it here. Yeah. So w, let's say y given x. So this is in the product form, let's say. Okay. So then there are two arguments here. I mean, two things here. Okay. So an argument of this function h here are two power distribution. Okay. And then this entropy, this is a function. Okay, is a concave function. This is also a concave function. This is concave function. Now I have to mention with respect to which one. This is a convex function with respect to the distribution p. Oh, not is this is not y, this x. Px. Okay, with respect to px. So to this px, it is concave. And the third important property is entropy h of y given x. Okay, which again I can write y. Okay, why it is why I'm writing just w given p. Okay, this is px and this is w means y given x. See, this is how it is defined. So you can see here it is expectation or with respect to distribution of x, but expectation of h y given x. So this is how it is defined. Yeah, this is how it is defined. You see how it is defined. So it depends on p and different h y given x, but this x is small, y is capital. Yeah, so average value of that. Okay, or the self information you can say. Oh, sorry, not self information, the conditional self information. So the entropy, this conditional entropy, let's say, or you can just write this is the conditional entropy. Conditional. So it is, I mean, this also defined in terms of two distributions. Okay, so this function is also is concave with respect to the channel, with respect to the channel w, let's say yx given x. This is what is the channel. Okay, and it's a linear function, and linear with respect to the input, with respect to px. Okay, so these are the main theorems we need to prove. The proofs are very, very simple. In fact, proof is just the definition of a concave function. That's it. So Let us prove the first one first. Okay, but see here, so all this theorem, all these results in this theorem, that makes sense only when you talk about the point-to-point communication system. Okay, otherwise this doesn't make any sense because you define entropy of a random variable, but here entropy of a conditional is entered, but this is defined in terms of the channel. So this W is missing unless you correspond to a communication system. This W is missing. Okay, so yeah, so you always need communication in the sense of communication system. We interpreted what is the meaning of this term, and this term. Now we are saying what is the property of these functions, because this entropy can also be considered as a function. So yeah, let's say prove this. First of all, I will prove one, which is that convex entropy is a convex function. In fact, it's a strictly concave function with respect to the probability distribution of x. Okay, so what do we want to mean? So what do we want to prove then? We want to prove that it is convex with respect to the probability. Okay, so that means you can say okay, h of, okay, let's say, okay, so let's say let p1 and p2 be two probability mass functions, let's say, or probability mass functions correspond to different random variable x1 and x2 on the same sample space. Okay, by the way, it has to be same sample space, otherwise this addition, okay, I missed that, but this addition will not be defined. Okay, like x1, x2, this addition will be defined only when this and this are the same dimension. Okay, so when I say it is a distribution space, the distribution space over the same sample space. Okay, meaning you only are defining different probabilities for different different outcomes. Okay, you are not changing the outcomes. Different outcome means you have set of outcomes. Okay, for each a probability mass function defined means all the probabilities corresponding to each of these outcomes is defined. Take another probability mass function, then another set of probabilities is defined for the same sample space. So sample space is fixed, otherwise this will not be defined. Yeah, so P2 PMX, okay, corresponding to some random variable x1, x2, to random variables x1 and x2, okay, associated, let's say, with some associated with a sample space, some S, let's say. Okay, then what I need to prove? Okay, then convex concave meaning I need to prove the other one, right? So I need to consider some kind of lambda p1 plus some 1 minus lambda p2. Okay, I need to do that, and then I need to prove what? H of this, okay, is less equal to lambda times p1, h of p1. If it is convex, so then I have to prove that it's scatter equal to concave means it's the opposite one. So alpha of hp1, okay, plus not alpha, but it's lambda of this plus 1 minus lambda times h of p2. This is what I need to prove. Okay. Now, does anybody have any clue how to prove this? Okay. So, yeah. Does anybody have any clue how to prove this? We have to use Jensen's inequality. We have to use Jensen's inequality. Okay, so for example, this star. Okay, what is this star? H of p1 means what? Sum of px log px, p1x. Okay, minus you can also say. And here this term is like sum of px log p2x. Okay, so this is, we had to prove that. Now for any particular x, forget about the sum, what is happening? See, this is what we need to prove. So the claim is, I mean, the idea of the proof is, can we have this? So this is the question. In order to prove this, which we want to prove is, can we, this is my guess, that can we have this? Do we have some argument such that we can say that, I mean, okay, let me write this entire thing as P, okay, otherwise every time I have to write this. So H of this P, okay, means what? Px, okay, log Px. And then sum of minus and everything is there, okay. I'm just taking for any particular x, okay. This should be bigger or equal to lambda p1x log of p1x plus 1 minus lambda p2x log p2x, okay. But can we have this? What is happening here? This is the function. This is the function, same function. And this is a function. Sorry. Or in fact, this entire thing is a function of x. What is that? What do I mean by this? I mean, let's say if you define a function fy, which is, let's say, y log y. So whenever y is equal to some px, let's say, so it is px log px. So this entire thing can be considered as a function. Okay. In fact, it's a real valued function for any y. If you give me y, then log of y. Okay. So whenever px here, for example, I mean, in the definition here, okay, so we already assume that 0 times log of 0 is equal to 0 and so on. Okay. So wherever entropy is defined, so there we are defining. But what about this function? This function, what is kind of function is? Is it a convex function, concave function? What is that? So y here, so f is basically a function from 0 to 1 because y is varying from, y is px here. So 0 to 1 to some r, you can say. So what kind of function is this? If y is equal to y log y. Okay, you can prove that this is how to prove that a function is convex. This is a convex function. How do we prove one function? Okay, one way is to show the definition, but do you know anything else, any other property which can prove the convexity of function? And we can prove that this is, what is this? A convex function. Now, since this is a convex function, now property of convexity, what can we say?
Sir, if double derivative of function f is greater than 0, then f will be convex function.
Okay, but do you need, so for this theorem to be true, whatever you mentioned, do you need any additional conditions on the function or the domain of the function and so on? Okay, so
Connectedness.
you can think about that. This is okay. This is how to prove convex function. We are not going to talk about that here. Okay. So let us say you know how to prove a convex function. Then can you prove that this is a convex function? If this is a convex function, so it satisfies the property of convexity. So that means what? And then apply. So is it a convex function? Then if it is a convex function, then apply just the Jensen's inequality. Convex function means what? In fact, it is. You can also prove more than that. You can prove that it is a strictly convex function. Strictly convex function. You can check it this, okay, not a problem. Now, if it is a strictly convex function or just a convex function, I can always use Jensen's inequality on this function, right? So if I use the Jensen inequality, what was that? This was this expectation. Expectation of f of x is bigger or equal to f of expectation of x. So if I do that, so expectation of f of e of x means e of px here, let's say, okay. So that px log, anyway, so what is f of ex? What is the expectation of x? That, and then you have to apply the function f, so oi of log of px. So that means px log px. So then this is actually achieved. You can see that this is achieved by using Jensen's inequality. Okay, what is Jensen inequality? Expectation of
Expectation of function is greater than equal to functions of expectation.
Okay, expectation of function. Sometimes the pen doesn't work. Okay. Is less equal to or bigger equal to?
Greater than equal to.
This one? This one?
Yes, sir.
Okay, now if this function small f, let's say y, f of y is equal to y log y, which is a convex function. So if I apply that, what can I say? Can I say that this inequality is true or not? क्या हुआ?
Sir, if we take this big X equals to lambda 1 p1x plus lambda 2 p2x and then use it, then on the left hand side we will have what we need. On the right we have log of something, and that I think can be like solved further using the property of log, convex property of log.
Okay. Anybody? Anyone else? Anyone else? This p, by the way, this p is equal to lambda p1 plus 1 minus lambda p2. Okay, I think we have to find that, yeah. And we need to prove this. Anybody wants to try? Anuj, are you here? Anuj? Gautam? You want to say something?
Yes, sir.
हाँ बोलो. बोलो क्या है ये, होगा या नहीं होगा, क्या होगा ये? What do you think?
So we have to go step by step using definition, then we can get result.
You can get. But can you tell me right now, or you want to try later on? Oh, why my pen is not right?
So in this, sir, basically we have to combine some definition and then we can get.
Okay, so let me write this as a homework. If you don't get it, then we can discuss it again. But you can give it a try if you want to try right now. I will take a break for 5 minutes because we are continuing. Okay, homework. How this can. Now, if this is proved, then everything is very simple. You just have to take the sum over all x. That's it. That's it, and then you don't have to prove anything. So once this is done, then So let me write it here. Then taking sum of both the sides over all x, okay, gives the desired result. I mean, if you take the sum, then it will give you the probability in this the entropy for each p1. Then this will give you the this is for the probability. This one. So this will give you this one corresponding to this p, and if it this should be the other way. So if you take the sum, then this will give you this. This take the sum, this will give you this. Take the sum, then this will. So this is the main thing actually, which you want to prove. Anyway, so let me leave it as homework. If you want to try for some time, you can try it right now. Otherwise, anyway, so this can be homework. And then the second result is about concavity of the entropy, okay, of y, but the concavity is with respect to px. That means what we need to show. Same thing here. Let's say we have the same condition assumptions. So let p1, p2, p1 and p2 be two probability mass functions, and then p is lambda, p is some let's say so yeah, let's say p is equal to some lambda p1 plus 1 minus lambda p2. Then what do we need to prove? That h of p, that means h of lambda p1. Oh, p here, w is already there, okay. So that means h of lambda p1 plus 1 minus lambda p2, let's say, times this w, okay, which you can show that this will be nothing. This will be nothing but this lambda p1 w plus 1 minus lambda p2 w, and then you have to show that this is true. Lambda h p1 w. So w is fixed everywhere, okay, you are not changing it. Lambda h of p2 w. This is what you have to show. But it can be done just like this way. This way. Same thing. And similarly, you can prove the third one, okay, also the third property also. So these are the main theorems, main properties of entropy. They are all concave functions of the probability distribution, except the fact it is linear. Linear is also convex, by the way, with respect to the probability of x here. Now we'll introduce another concept. Actually, I'm running very slow, but now we have another concept which you need to introduce, and this is also a very handy tool to prove many inequalities for entropy and mutual information. And this concept is called divergence. Okay, so this is a new concept called divergence. Okay, this is divergence of two random variables. Okay, so it is kind of a notion of a distance, okay, or a difference. Let's say instead of distance, let us call it this difference of two random variables. Okay, so let x and y be two random variables, and then we define. Okay, so it is when you say this. So let us say px and py are the corresponding probability mass functions. Then this is called then the divergence, or it's also called Kullback-Leibler information. LEI L LEI BLER, Leibler information, or it is also called relative entropy. In fact, it's actually called Boltzmann relative entropy. Entropy, okay, of x and y is defined as follows. Or it is denoted as actually this, because the difference, so you can say it is like d of x and y. So this notation you say double bar, okay. This is the same thing as denoting that this px and then double bar qx, and this is defined as this sum over x, okay. X is a sample space here, and px, so yeah, x and y random variable here. Let me write over the same sample space, over the same sample space. I mean, if you want to compare two different random variables, of course the sample space have to be the same, but let me write it explicitly here. So it is the px, okay, and then log of px's. This is how it is defined, okay. Of course, here can be situation where like kx could be 0 or px could be 0, okay. So with the assumption, with the convention that 0, if it is this kind of situation, 0 log 0 by b, then we'll assume that this is 0, whatever be b, okay. B can be bigger or equal to 0. So b also could be 0 actually, and a log, let's say a by 0, this will assume plus infinity when a is bigger than 0, okay. And you can of course change the, so this is in general bits, because you can say this base log, the base of the log is 2, but you can define it for any, let's say any base. So you throw up that. So here what you can do is, here you can write one a.
Sir, what
So
is
this,
capital
yeah.
QX?
Capital QX is the O, so it is capital QY.
PY.
Yeah. So yeah. In fact, you can write also X, because here you are taking what the sample space. So sample space, I said, it is the same. So you can write. So it is the probability mass function about the same sample space. Okay, like S1, S2, Sn, let's say. So the random variable will take those values. So you can write even X. Okay, I think that will be better to write it, because the sample space is same. I think it will be better to write it as X itself, no problem.
Sir, in the beginning, you written corresponding to capital X, the PMF is PX, and corresponding to Y, it's PY.
Oh,
So,
okay. So let me change this. Okay, with the same sample space, so it can be written as QX also. That's not a problem. I mean, because this PMF depends only on the sample space. Okay, what are the samples? The sample space will take the different probability values only. Okay, so now what I'm saying is, yeah. So the sample space is same. So you can say like it is just the different probabilities, okay, of this thing P and QX. I mean, probability mass function. So then you can define this. Okay, so so you can change this base also, and accordingly you can have any base, and accordingly you can convert from one base to other base. Now we'll well, now here we'll mention one more inequality, which is actually I'm not going to prove. So why I'm introducing this concept? Because in this concept, we will prove some interesting fact about mutual information and entropy. So that's why I'm introducing this concept. Now the question whether it is a distance, or some people will call it a distance, but okay, this will give a notion of distance. Okay, in fact, it is called a geometrical notion of distance in the distribution space. Okay, but so if you want to study the geometric theory or the differential geometric theory of statistics, then this will play a big role. Okay, but let us not go into that. So this will induce a geometrical notion of distance, okay, in distribution space. But probably you can see that in general. So D here, this is just an observation. Let's say observation that in general, so dx y is not equal to dyx. So why? Because this qx will be in the denominator here, qx is in the numerator, and this px will be also changed to qx. So in general, this is not. So, but in the notion of distance, we always have like distance from a to b is equal to b to a. Okay, this is a notion of Euclidean geometry, but there are other geometries also. Okay, the geometry is always turned out by Euclidean. Okay, so this distance, okay, this notion of difference or distance, okay, this will play a big role if you study differential geometric theory of statistics. So, and then here the space, this induce a concept of distance in the space of distributions, which is known as a distribution space. Okay, so we are introducing this concept to show some property. We'll define, and then the question is, this is okay. This is a function, you can say, like, which will give you a value given x and y. So given px and qx, it will give you a value. Okay, then the question is, can this value be negative? Okay, if it is negative, then it cannot be a notion of difference or distance, right? So we'll actually show that this is always bigger or equal to 0. But in order to show, we can assume impact without using the inequality. There is something called log sum inequality. Okay, I can just mention it here, but without using that inequality also one can prove using Jensen's inequality. But let me just, for the sake of completeness, let me just mention what is log sum inequality. The proof is very simple. You can find it in this Thomas and Thomas book. But let me just say what is called a log sum inequality. Okay. So what I'm trying to say is, using the log sum inequality, or maybe okay, let me just give you the statement of this. So for non-negative numbers, let's say a1, a2, dot dot dot. And this is a very important inequality, by the way. I mean, many places you will see in information theory, this inequality is used. And let's say a is equal to sum of ai. Okay, I equal to, let's say, 1 to infinity. And assume that this series is convergent, it is finite. B is, let's say, sum of bi. Okay, I equal to 1 to infinity, and let's say this is also finite. Then one can show that sum over this ai log ai by bi. See, this kind of same situation is happening here. This is, let's say, it is ai, it is bi. Okay, same situation. ai log bi is bigger equal to a log of a by b. One can prove this. Okay, let's say what of I. Let's say I equal to 1 to infinity, and this inequality becomes an inequality equality. So the equality holds if and only if ai divided by bi is fixed for all I. So is constant for all I. So this is what I'm not going to prove it. This log sum inequality is very simple to prove. Then using this, I mean, you can see it in Thomas and Thomas. It is clearly, the proof is clearly written. Okay, so there you go. Using this inequality, in fact, without using this inequality, also one can prove using Johnson's inequality. I'll give you both proof maybe. So the most important, let's say, result is So this is the result. Okay, most important result, that we need to show that if this induces a concept of difference or distance, then it has to be a non-negative number. So that d of x given y, which is, let's say, d of p and q. Okay, this is d px qx, let's say. So this is bigger or equal to 0, and equality holds. Equality holds if and only if p is equal to q. This is what happens. Okay. Now proof is just one line. Proof is just one line if you just use log sum inequality. Okay. So let ai is equal to pi. Okay, pi means p of x. So x equal to px. So you let pi, and bi is equal to, let's say, qi. Okay, means the I is the outcome here. Okay, where I is in the sample space. Okay, sample space corresponding to x and y. So corresponding to p and q, corresponding to p and q. Then what about the sum? Sum of ai. Sum of ai is equal to what? What is sum of ai then? Guys, can you hear me?
Yes, sir.
Yeah. So what is the sum? Sum of ai is equal to what?
So 1.
Yeah, 1. This is a probability distribution, right? So the sum of bi, this is also equal to 1. Now use Jensen's inequality. So a and b, so which is a here. This is a here in the Jensen, not Jensen inequality, but it is log sum inequality. This is a and this is b. The both are 1. So then what? Log of 1 means 0. So right hand side will be 0. Left hand side is what? Left hand side is just the concept of the distance, d of x given y. So it is proved that this is bigger or equal to 0. Okay, so you can use this log sum inequality as this, and otherwise you can have an alternative proof. So you just let that some other y, a new function y, let's say, which is qx by qy, px. Then what is that? D p given q is equal to over all x, px, or maybe all I, pi log of minus qi by pi. Okay. See, I have written minus here. Okay, that's why I reverse the term qi by pi instead of writing pi by qi. So this is log of, then this is log of a function y. Okay. So then this is bigger or equal to minus log of. Okay, my question will be why I am writing this, and my question is this: pi qi by pi. So here the observation is this inequality is obtained after a lot of step jumps. So here you can show that this log y is a convex function, and using the Jensen's inequality. This can be proved. Okay. So, and now I'm going to prove the most important result, okay, of entropy. Okay, using this concept of D. Okay. So when the question is, what is the maximum value of the entropy? So here is the question, and this what is the maximum value? What do I mean by this? On which the maximum is taken? I mean, on which set it is. I am talking about the maximum. What is the argument here? Argument is the distribution space, maximum value of entropy. Say, when I defined entropy, we talked about h of x, which is of p of h of p, basically probability distribution. Okay, so this was my distribution space. So where everything is a probability mass function. This is a probability mass function. This is a probability mass function. So the thing is, h, whenever I take this h of p, so which is sum over all px, okay, log px minus over all x. So this each p is coming from this space, distribution space, so space of all distributions. Okay, so then I'll have a corresponding value for each of this. Let's say this is p1, p2. If it is countable, you can write it like this, right? P1, P2, and so on. All that is not countable. So P1, P2, like if you take different kinds of distributions, so a P probability mass functions, you have different entropies for the same random variable. Okay, so depending on how the probabilities are different for each possible outcome, you'll have a notion of entropy, a notion of value, how much uncertainty is there. Let's say. Then the question is for which distribution it gives you the maximum value. So maximum uncertainty is there. Of course, as we said, as you have seen in the example of the tossing of a coin in the first week, or maybe the second week, so we have found out that if the probability of getting head and probability of getting tail, they are equal, which is half, then the entropy becomes maximum. So if you just recall the picture, okay, it's like this. Oh, it's from 0 to 1, so it is like this. Okay, this was the picture, and we said, okay, this is maximum when p is equal to half. Okay, this was the h2p, this function. Okay, if we just consider this, and this is p, and this is from 0 to 1. Okay, so you can say that p equal to half, meaning this is the uniform distribution of the head and tail. In fact, this is what happens in general, that this takes the maximum value, entropy is maximum when this p is the uniform distribution, the probability is the uniform distribution. So this is an important result, which is the maximum value of the entropy, which says hx, okay, hx, h of x, let's say entropy of x is less equal to the log of mod of the sample space corresponding to x. Okay, why it is a sample space corresponding to x? Because this is what you will get when you take the uniform distribution. So with this is always less equal to case with equality only if, okay, x obeys the uniform distribution. Means all outcomes are equally likely. Okay, so how to prove it? Proof is also very simple, just using the definition of the relative entropy. So the proof is, let px is any in the relative entropy definition, that's dx given x double bar y. It is just any px, and let's say qx is equal to 1 by mod of sx. So it is just the uniform distribution. Let's say equally, like all equally, like s is like if it has n number of course, say here we are assuming the uniform distribution. Okay, this is defined. This is a very important observation here. The uniform distribution is only defined when your sample space is finite. If it is infinite, there is no uniform distribution. The uniform, this is very important observation. This is undergraduate probability. So the uniform distribution or equally likely is defined only when the sample space is finite. Okay, so then what do we have? Then d of p given q this is equal to, you can show that this will be log of mod of Sx minus Px, okay, minus h of Px. Now, since this is equal to bigger equal to 0 as we proved earlier, okay, then this is always the case, okay, this is proved here, and you can show this is equality only if x is uniform, okay. So this is one of the most important results about entropy, as if it is a function of all possible PMFs, and the question would be what is the maximum entropy? That means on which PMF, on which probability distribution of x, when, what are the probability distributions of the letters involved in the information source, such that the entropy uncertainty is maximum, and that is when all the letters are equally likely. Okay. Another important result I want to mention here, using this relative distance, I will see why it is important if I state it. So if you consider any random variables like a sequence of random, let's say x1, x2, dot, 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 xn, then the sum of these uh, entropies, okay, sum of the entropies is always bigger or equal to the joint entropy. Or just write x1, x2, dot, 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 xn. Sum of this is as a joint random variable, whatever the uncertainty is, that is less than sum of their uncertainties. Can you give any example where this could be useful? Anybody? And this equality holds only if xi's are independent. Xi's for I equal to 1 to n are independent. Can anybody tell me what is any application, like where this kind of result is very, very useful? Okay, the proof is very, very simple, by the way. So let you just assume that this Px is just the joint probability distribution on the mass function, and Qx, let's say, this is their product. So P of x1, P of x2, dot, 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 P of xn, and then you can see that D of P given Q, this is sum over x, Px, log of Px by Qx, and we already have proved that this is bigger or equal to 0. From here, it shows that this is the case. Anyway, so proof is obvious, but can you give any scenario where this could be very, very useful? Anybody? Okay, so think about it. Homework is give an example of a situation where this inequality is useful. Okay, another important result, okay, which I must mention. I mean, this can be proved using the relative entropy again, which is, we talked about mutual information between two outcomes like AI and BJ or AK and BJ. Okay, how much information you want to quantify that? What is the amount of information about AJ is known when you know that BJ has occurred, or AK is known and BJ has occurred, or how much information how to quantify the information like what is known about BJ when AK is known, let's say. This is the connection between input and output outcomes. Then we said that in the formula, this could be negative, the mutual information could be negative. But it is surprising to see that the average mutual information, that means given any two random variable x and y, I x semicolon y, average information, this is always non-negative. And this has implication. Now, see, recall, we have written this initial information in terms of entropies. So this implies, I'll just write this implies. From that inequality, you can show that this is always hx, and this is a very, very important inequality. And this inequality, the equality holds if x and y are independent. Obviously, why this is very important? Why this is an important inequality? Can anyone tell me? Proof is again, the proof is again obvious. Okay, so proof is again using this Kullback-Leibler distance or the relative entropy. So you just have to put, let's say, pxy is equal to pxy, the joint one, and let's say qxy is their product, and pyy. Okay, then see that d of p given y in q is actually equal to I x given y. So the immature information where we have defined, this is exactly the difference between two random variables, which is nothing but the joint and the product. Joint distribution of xy and the product of distribution of x and y. So, and since this is bigger or equal to 0, we already have proved that this is bigger or equal to 0. So automatically it implies that mutual information is always bigger or equal to 0. Okay, so yeah, can anybody tell me why this is important? Gautam?
Yes, sir.
Can you tell me why this inequality is important? H of x given y is less equal to h of x.
So it gives the bound of uncertainty of x given y.
That is okay. That is okay. But in the sense of communication system, what is the meaning of this?
Uncertainty can be at most self-information.
What is this left hand side is actually a conditional entropy. And if you want to speak about uncertainty, it's uncertainty of what? This is very simple. This is very, very obvious result. This inequality gives very obvious result, which we have been always, we always say this when we introduce the notion of conditional probability. What do we say when we introduce non-conditional probability? When we define px given y in an undergraduate class, let's say, we always say px given y is, or let's say pa given b. Let's say b are two events. Then we say p of a given b, a and b divided by pb, provided pb is bigger than 0. So we always say that when you supply additional information b, okay, then the probability of a given b is not same as probability given a. Okay, so in general, probability of a given b is not same as probability of a, and they are same if and only if a or b are independent. So now here, what is x given y is less equal to hx. That means whenever you have an additional information, I forgot about information in the generic sense. So you have additional things, additional stuff. Okay, so when y is given, okay, then the uncertainty reduces. That is what it means. So it is totally compatible with our usual understanding of this fact that if I give you additional information, then the uncertainty will be, there is a chance that uncertainty will be less. It cannot be greater. So this is what it supports that intuition, that uncertainty about x, okay, or the entropy of x, okay, that reduces, okay, that reduces when some additional information like y is supplied to you. So in the sense of point-to-point communication system, once I know the outcomes, okay, the uncertainty about x is reduced. Okay, unless I know this y, this is more. I mean, I don't know which let's say letter will be sent, will be received once you send a particular, let's say, letter, because there are conditional probabilities in the channel, there is a noise in the channel, you don't know. But once you know the output, obviously then the uncertainty about this x, okay, that little bit reduce. And this intuition is now approved by this simple inequality that hx given y is less equal to h of x. Yeah, so if you have any question, you can ask me. So we'll now in the class, we'll stop the recording. Or if you do you have any question? Okay, so yeah. Does anybody have any question? So today I thought I'll start coding, but unfortunately I could not start it. Yeah, we spent a lot of time regarding convexity, and then somehow we managed to finish everything about information before we are able to start coding thing. Now we'll start talking about coding, how it can be done, and what is the role of information in coding. And then again we'll come back to information, and we'll see how to develop some more understanding about this information theory, so that we can have a better understanding about coding and about communication channels or communication systems. Okay guys, so since there is no question, let us stop the meeting here, and then